Alright, in this video we'll be taking a brief look at radical reactions. And how they can be used in chemistry. The first thing we need to do is go back and look at the allelic radical, which you may remember is resonance stabilized. That when we have this carbon in the allelic position, we have a radical here that we can move this radical up. And remember, radical mechanisms, that when we're moving a radical, we only use half an arrow. So I specifically left off the other part of this arrow. And so in order to make the double bond here, we need to move one of these double bond electrons over by another radical, and the other electron will move to that spar carbon to form our new radical in the other resonance structure. And we can get back to the first resonance structure by doing the reverse. And so this is how the allelic radical can be resonance stabilized. And when it comes to the stability of radicals, allelic will be more stable than a tertiary radical, which is more stable than a secondary radical, which is more stable than a primary radical. So it's similar to carbocation stability, and the tertiary is more stable than secondary, which is more stable than primary. So another thing that we need to remember is that allelic systems will react with bromine in two different ways. And so if we have an allelic molecule, we can react that with bromine in carbon tetrachloride to produce this molecule, where we add bromine across the double bond, going through a bromonium ion intermediate, which you should recall would look like that. And then the other bromine can open up the ring and produce this dibrominated compound. The other way that allelic molecules can react with bromine is use dilute bromine and ultraviolet light in order to get the reaction to go. And there, instead of producing this dibrominated compound, we'll substitute one of the hydrogens at the allelic position with a bromine. And so we have the addition of two bromine molecules across a double bond when we're using concentrated bromine, and we have the substitution at the allelic position when we're using dilute bromine. And this bromine will always add at the allelic position, not to either of the double bonded carbons. But remember that the allelic radical is a resonance stabilized, and so we can get the bromine over here if the double bond were on the left. So we'll go through the mechanism for this second reaction to explain why it's different from the concentrated bromine reaction. And this mechanism is a multi-step reaction. And step one is called the initiation step. Then we start with taking a molecule of bromine, and when we hit this bromine with ultraviolet light, we'll break that covalent bond so that each bromine takes one electron. And so we'll generate a pair of bromine radicals. This initiates the radical reaction by creating the radicals. Once we get these radicals, then we have step 2, propagation, where now if we take our allelic molecule with its allelic protons and a bromine radical that we produced in the initiation step, then the electron from our bromine radical can attack, and this is how we show the attack on one of these protons, is that one of the electrons from this carbon-hydrogen bond will come up and bond with the electron from the bromine radical. The other electron from the carbon-hydrogen bond will move back to the carbon atom and will produce the allelic radical, which, remember, is resonance stabilized, plus HBr. And the formation of hydrobromic acid will become important a little later in the video. So I've run out of room, so we'll make some more room here. And we'll continue with the propagation step. We have our allelic radical, and we have another molecule of bromine. And what can happen here is the allelic radical can attack that bromine, and so one of the electrons from this bromine-bromine bond will be used to generate a new carbon-bromine bond, and the other electron will move over to the other bromine. So now we form the brominated allelic compound plus another bromine radical. And this bromine radical is available to come and react with another molecule of our allelic molecule. And so essentially it's a chain reaction that when the allelic radical reacts with the bromine molecule, it produces another bromine radical that can produce another allelic radical. And then finally we have step 3, which is the termination step, but this happens relatively rarely. And the termination step is when one bromine radical encounters another bromine radical, and the two radicals react to regenerate a molecule of bromine. And so that will destroy the radicals, and the radicals will no longer be available to react in the solution. We can also get a byproduct of the allelic radical. If we have two allelic radicals that encounter each other, then in a similar mechanism, we can get those radicals to react and form a new carbon-carbon bond. So this is another way of eliminating the radicals from the reaction, and we would produce this compound as a byproduct of the main reaction that we're trying to achieve with the bromination. And so there are three problems that we encounter when we try to do this reaction. And problem one is that it generates hydrobromic acid. And that hydrobromic acid can add across the alkene. And so we would get a reaction between the hydrobromic acid and the alkene to get a Markovnikov addition of the hydrogen atom and the bromine atom across that double bond, and we would end up with a different product than we want. The second problem is that it's difficult to produce dilute bromine solutions. And so controlling the concentration of bromine so that we get the radical reaction instead of the reaction through the bromonium intermediate is problematic. And problem three is that delocalization of allyl radicals leads to multiple products. But we can solve problems 1 and 2 by using NBS or N-bromosuccinimide. Actually, it might be with an I. And again, the structure of the N-bromosuccinimide is this. And so we can use this to generate bromine radicals in a similar mechanism to how we can use bromine, the dibromine molecule, to form bromine radicals. That we can take this NBS, react it with ultraviolet light or peroxides to produce these bromine radicals. And so NBS will end up producing a low concentration of bromine radicals because the NBS is not very soluble, and so it ends up producing there'll be a very small concentration of NBS in the solution at any time, and therefore it will produce a very low concentration of bromine radical. And that is a way of getting that bromine radical at a low enough concentration in order to overcome this problem too. And so an example, again, we have a allylic compound. We react that with NBS in carbon tetrachloride with either ultraviolet light or peroxides. We get our substitution. We substitute one of the allylic protons for bromine again. And the mechanism with NBS is essentially the same as the mechanism I showed with the bromine, the Br2. Except, again, we're forming the bromine radical from NBS rather than Br2. Now, another advantage of using NBS is that it will trap the HBr that is the hydrobromic acid that is produced so that we can prevent the addition of hydrobromic acid across the double bond. And the way that happens is that the NBS will react with hydrobromic acid to produce this molecule. We've exchanged this bromine for a hydrogen, and we also generate Br2. So this solves the hydrobromic acid problem, but we'll still end up with multiple products. And up to this point, we haven't seen multiple products because we've only been using this propene molecule. But if we use a more complex allelic molecule, then we'll see multiple products. For example, if we use this with NBS and carbon tetrachloride, ultraviolet light, we can produce this allelic radical and its resonance stabilized form with this other allelic radical. And then this first radical can react with bromine to form this product. The second radical can react with bromine to form this product. And so we can get two different products from this one starting reactant. So we'll finish up with some more examples of radical reactions that we've looked at previously in the class. And that one of them is the halogenation of alkyl benzenes. So if we have, like, let's say toluene, for example, and then we have these protons on the toluene. If we have a halogen radical, such as chlorine or bromine, then we can pull off one of these protons through a radical reaction, and we can generate a benzylic radical. In this benzylic radical, it will always form at that first carbon on away from the benzene ring. That this will be a conjugated system, so it should be fairly stable. And then once we have that radical, it can react with another halogen radical to produce the halogenated product. And so, for example, if we use toluene plus chlorine with ultraviolet light, we could also use peroxides again to generate the initial chlorine radicals. Then we would produce the chlorinated toluene plus HCl. That if we were to use a benzene with a longer alkyl chain, then again we would get halogenation, and again it would occur at that benzylic position. And so we would always halogenate at this benzylic position, one carbon away from the aromatic ring. So now we'll recall a couple of other radical reactions that we mentioned. You might remember that hydrobromic acid plus peroxides leads to the anti-Markovnikov addition of hydrobromic acid across the double bond, because this goes through a radical mechanism similar to the other radical mechanisms, so that we can, if we don't need to know the entire mechanism for this, but it involves radicals rather than a normal addition of hydrobromic acid across the double bond, and that's why we're able to get the anti-Markovnikov addition. The other one that we might recall is the dissolving metal reduction of an alkyne. So we can use sodium in ammonia or lithium in ethylamine. And we'll end up getting the E alkene rather than, so this is a hydrogenation reaction, but it produces the trans isomer rather than doing hydrogenation on a platinum catalyst where we would get the cis isomer. So with that, that's essentially everything we need to know for this class about radical reactions, and which makes it the last and only video from Chapter 10, and the last video of the semester. So hopefully you enjoyed the class, or what there was of it, and that we've all learned something about organic chemistry, and we hopefully survived this online teaching experiment. Thank you.